This brings us now to the fundamental theorem of arithmetic, which states that every natural number can be expressed as a product of prime factors. Let's have a look at some examples. Let's take number 6. We can factorize it into smaller components using a very simple column factorization technique. The smallest number that 6 is divisible by is 2, and that will give us 3, and 3 divided by 3 equals 1. So we can write 6 as a product of 1 times 2 times 3. This is what we mean by product of prime factors. All these numbers here are prime numbers, and all these numbers are factors of 6. They divide into 6, and therefore we call them prime factors. This is an example of factorizing a number into a product of prime factors. Let's have a look at another example. Say 10. 10 is divisible by 2. That'll give us 5. 5 is divisible by 5, and that'll equal 1. So that means 10 is made up of the factors, prime factors, 1 times 2 times 5. Let's take another example, 28. Well, 28 will divide by 2, that'll give us 14, which will divide by 2 to give us 7, which will divide by 7 to give us 1. So that means 28 can be expressed as a product of 1 times 2 times another 2 times 7. Again, you see 28 here is expressed as a product of prime factors. All of these numbers here are prime numbers, and they're all factors of 28. This is what we mean by the statement in the theorem, which says every number, natural number, can be expressed in this fashion into a product of prime factors. Now, if you examine it a little closer, you will find that 28 is divisible by the following set of numbers. 1, it will divide by 2, it will also divide by 4, and it will divide by 7, and if it will divide by 14. Now, these numbers will all divide into 28, and therefore we call them proper divisors of 28. If we now add all these numbers together, we get a sum, which is 1 plus 2 plus 4 plus 7 plus 14. If we add them up systematically, 1 and 2 is 3, plus 4 is 7, plus 7 is 14, plus 14 is 28. Well, what do you know? All the proper divisors of a number add up to equal the number itself. When that happens, we call such numbers perfect numbers. Perfect number is a number whose proper divisors all add up to equal the number. Now, there are not many numbers which we call perfect numbers. There's only a few of them known to mankind, and the smallest of these is 6, is a smallest perfect number. The next smallest perfect number is 28. The one after that is 496, and the one after that is 8128. These are the 4 perfect numbers which were known to the great mathematician Pythagoras. Now, Pythagoras also discovered the connection between numbers and music. Pythagoras found a relationship between musical harmony and numbers. He experimented with a vibrating string and found that to get a pleasant, harmonious sound, the string must be divided into exactly whole numbers. For example, into exactly 2 or 3 or 4 divisions. We can illustrate this using a modern keyboard and an oscilloscope. Here we have a ground note which is represented by a wave which has one peak. This note here is an octave above that. It has two peaks corresponding to double the frequency. This note here is an octave above that again, and that has four peaks or 4 times the frequency. The use of chords in music is an example of having the right numbers to make the right sound. This chord is a third, and this is the fourth. And this is the sound of the perfect fifth. If you haven't got the right numbers, it doesn't sound harmonious. It sounds discordant, like this. Using modern technology, we can represent, play, and control music by numbers. Pythagoras also found that a certain ratio is incorporated in the beauty and perfection of nature. If we take a straight line AB and locate a point C on this line so that the ratio of the smaller part is to the larger part as the larger part is to the whole, we will get what the ancient Greeks called the golden section. If we rearrange this so that the larger is to the smaller as the whole is to the larger, we find that the ratio of AC to BC is the same as AB to AC, which equals 5, the symbol we use to describe this ratio. It was called the golden ratio by the Greeks, and also divine and perfect proportion. A rectangle formed with the sides in the golden ratio is called a golden rectangle. It is commonly found in the science, art, and architecture of the classical Greeks. The Parthenon, for example, was built incorporating the golden ratio. There is evidence that most people unconsciously favor golden dimensions when selecting business cards, greeting cards, mirrors, parcels, and other rectangular objects. If we begin with a golden rectangle and build a square corresponding to the height, we get another golden rectangle inside the original, and this process can continue indefinitely with a new golden rectangle forming each time. If we join the corners of each square with an arc, we get a curve which very closely resembles a logarithmic spiral. This aesthetic form is admired by many cultures. It appears in nature as snail shells, animal horns, flower heads, pine cones, etc. It also appears in many spiral-shaped galaxies and is the only curve which doesn't change its shape as it grows. In the year 1202, Leonardo Fibonacci, probably the most distinguished mathematician of the Middle Ages, published this famous problem. A certain man put a pair of rabbits in an enclosure. How many pair of rabbits will be born there in the course of 1 year if it is assumed that every month a pair of rabbits produces another pair and that all new rabbits begin to bear young 2 months after their own birth? We have 1 pair of rabbits on January the 1st. This pair will produce another pair on February the 1st and on the first day of every month thereafter. Each new pair will mature for 1 month and then produce a new pair on the first day of the 3rd month of its life and on the first day of every month thereafter. Let A represent an adult pair of rabbits and B a baby pair. We can use a table to keep an account. From the total number in the last entry of the 3rd column, we get the answer to Fibonacci's problem. There are 377 pairs of rabbits at the end of 1 year. The 3 columns of numbers that were generated in arriving at the solution comprise the terms of the famous Fibonacci sequence. One of the most striking features of Fibonacci numbers is their repeated occurrence in nature. One example can be seen in the natural descent of the male honeybee. As with rabbits, the population of drones is determined by the Fibonacci sequence. The count of petals in most flowers follows Fibonacci numbers. This one here has 5 petals. This one has 21, and this one has 34 Fibonacci numbers. If we take a pineapple and number the scales in order, number 1 being the closest to the crown, and number 2 the second closest, etc., 3 sets of spirals are evident. These form arithmetic sequences with the common differences of 5, 8, and 13. Again, 3 consecutive Fibonacci numbers. We now know that the matter in the universe is made up of some 92 naturally occurring elements. We classify them by atomic numbers, based on the number of protons in the nucleus of the atom. 1 proton is hydrogen, 2 protons, helium, 3 protons, lithium, 6 protons, carbon. The heaviest element is uranium, with 92 protons and 92 electrons. Nature is a numbers game, and I think that Pythagoras had a point when he said, all is numbers. We can illustrate exponentiation with a mathematical model. Let this circle be our basic unit. Base 2 means there are 2 circles together in a module represented here by a box. 2 to the exponent 3 means that each unit circle duplicates itself to produce another base 2 module, and each of these unit circles duplicates again to produce another module, which results in a total of 8 units.